All right, I'm going to talk about two incredibly important, really important metrics or measurements for the overall quality of a model. And these two metrics are referred to as the AIC and the BIC. And we'll talk about what they are, and we'll talk about how to use them. They're useful not just in time series, although they are exceptionally useful in time series, but their use actually generalizes well beyond time series to really just comparing any two models, whatever those models might be. Right, so we know from 512, right? 512 we talked about like like metrics that measure how well a model works. And we talked about even the idea of trying to maybe pick models based on how well they fit these metrics. So in 512 we talked about things like SSE, the sum of squared error, right? We talked about R squared. In 507 we talked about likelihood scores, right? And in particular, we talked about like the -2 log likelihood, and we talked about the likelihood ratio test, right? The likelihood ratio test was we looked at the difference in -2 log likelihood between two models, and that follows a chi-square distribution, and then we can use that chi-square distribution to compare the two models. However, the problem of using any of these metrics, right, whether it's SSE, R squared, or the likelihood function, at least in isolation of anything else, is that these metrics, these measurements, are always improved by adding variables to our model, right? We know this particularly for R squared, right? We really hammered that home in 512 when talking about R squared. We said one of the downfalls, one of the drawbacks of R squared is that adding variables to the model, right, practically always raises the R squared, right? Theoretically, it can never decrease. And so that means that using R squared, it's always going to pick the largest model, which violates, right? It violates what? It violates that spirit of parsimony, which is the heart and soul of model building. So what are the solutions, right? There is something called an adjusted R squared. We may or may not have seen that in our proc reg output. But more common solutions include these measurements right here. And these are measurements that evaluate the quality of a model while at the same time penalizing for extraneous terms. And so the measurements are the IC, the IC, the second C stands for corrected, so we call that the corrected IC. And then the third thing is the BIC. So the IC is referred to as, I don't know how to say that word, information criteria. And it is typically defined as 2 times K, so K is the number of parameters being estimated, minus 2 times the log likelihood, right? There's that likelihood function, or the maximized likelihood function. So we're going to elaborate on this in some upcoming slides, but let's look at this. Let me say now that when we're using the IC, kind of similar to the SSE, smaller is better. And so if smaller is better, we could see the penalty, right? That is, when I'm adding variables into my model, those variables now are more parameters that need estimating. So that K is increasing, it means the IC is increasing. Right, now also adding more variables into my model is probably increasing the likelihood function. Right, you've been exposed to the likelihood function in Stat 506. We'll review it, I think, next slide. But we want the likelihood function to be as large as possible. And adding variables will invariably increase that likelihood function, right? So when I'm adding variables, sort of two things are happening. That likelihood function is increasing, which shrinks the IC, but that K is increasing, which enlarges the IC. right? So that means that we only want to add variables up to the point where what they're adding to the maximized likelihood function exceeds the penalty that they're bringing to the model. Right, so again, the likelihood function is what? The likelihood function measures the likelihood of certain parameter values given the observed data, right? So loosely, we could think of it as, right, what's the probability of seeing, right, these specific parameters, right, given the data that we've just observed. Right, so the likelihood function is, right, what's the probability of, say, the mean equaling something, or, right, I guess in our case more likely, what's the probability of these betas, these regression coefficients equaling something based on our observed data, right? So this is something that you at least played around with a little bit in Stat 506, right? Think back to when you were looking at MLEs, right, maximum likelihood estimators, right? You were working with likelihood functions when you were doing that. So that ick is like a probability, and we want that probability as large as it can be. So right, larger is better. It's basically a large likelihood is saying that there's a high probability of this model occurring based on the given data, right? So it's kind of indicating that, right, that our model, our estimated model, is fitting that observed data well. So a good model should have a large L, or large likelihood, and right, that implies a large log likelihood, right? But we also want small k, which is that parsimonious idea. And so ultimately that will lead us to, right? So that I guess logic leads us to the idea that the smaller the ick, the better. Now, something to think about. How do we use this ick? Now, right, this is maybe something that makes us a little uncomfortable, but the ick is not a hypothesis test. It doesn't have a distribution, and so we can't derive a p-value. It's not going to tell us if our model is significant. It's not going to tell us if we use it to compare two models. It's not going to say that one model is significantly better than another model. It just gives us a way of ranking models. That is, it could be that all of our models are, quote, bad models, in which case the ick is just helping us pick the least bad model. Okay? So we want to know how it works. We do want to know some of its limitations. Right? But this idea of ranking models is its primary use. And you might say, like, well, why do I care? Like, why do I care? Because why? We've already, in a way, learned how to compare models. Right? In 512, how did I compare models? Well, in 512, right, we talked about this idea of the full model. We talked about this idea of the reduced model. Do you remember? And we talked about a chunkwise f-test as a way of asking the question, is the full model significantly better than the reduced model? Right, so we had that chunkwise f-test. In 507, we developed something a little bit more general than that chunkwise f-test. We developed the likelihood ratio test, and we said in 507, if I want to compare two models, I could look at their -2 log likelihood, and I could look at the difference in that -2 log likelihood, and that I can show follows a chi-square distribution. So I can look at the p-value of that distribution, and that p-value tells me whether or not, right, the larger model is significantly better than the smaller model. So that approach does work really well. In fact, that approach in a lot of cases is probably better than using the ick. However, that approach has a huge limitation. And what is that limitation? The chunkwise test and also the likelihood ratio test, they require that one function be a subset of the other function, right? Is that you have to be comparing what we refer to as nested functions. One of the functions has to be a subset of the other. Now, the AIC is really powerful because it allows us to compare models that aren't a subset of one another, right? So like the chunkwise test and the likelihood ratio test are often just saying like, all right, I have some variables in my model already. I'm thinking of adding some more variables to my model. Is this a good idea, yes or no? Or adding these extra variables, right, improving my model significantly. But the AIC allows us to just compare two very distinct and different models, right? For example, the AIC would allow us to compare an exponential smoothing model to an ARIMA model, right? Which can be two very different models. And it's not like one model is like just kind of the same model with a few extra variables. And so that's the sort of power and utility of the AIC. How do we use it? We can get a whole bunch of different time series models that are not necessarily nested into one another. We can rank them by their AIC, and we can then use that AIC to guide us to which model we think is best. Now, to help this idea of ranking and picking, let's consider that we have K models, right? And each of these K models has their own IC, right? So we have IC of the first model, IC of the second model, right? All the way to the IC of the Kth model. We can define the relative likelihood of model I as E to the power of the smallest IC minus IC of I, of model I, divided by 2. We can show that this can be interpreted as the relative probability that the ith model minimizes the estimated information loss from the unknown true distribution. So what does that mean? It's a little bit technical, this idea of information loss, but right, that is the idea behind the information criteria. So imagine we have three models. They have ICs 100, 102, 110. So our IC min, our minimum IC in this case, is the first model, which has a IC of 100. If I wanted to look at that that relative information loss for model 2, I would just do 100 minus 102 divided by 2. I'm going to get 0.368. So how would I interpret that? I would essentially interpret that as the second model is 0.368 more likely than the first model to minimize the information loss. So, right, I mean, more likely is maybe a little bit of a misnomer because it is less likely. We're saying that the probability that this is the thing that minimizes the information loss, it's about a third the probability of our best model, right? So I mean, in theory, we're picking the one with the smallest IC. So in theory, we're picking that model that has 100. But this extra measurement here allows us to kind of see, all right, well, how much worse is our second model? How much worse is our third model? And here we're basically saying that, yeah, like it's possible that the model 2 is better than model 1. Right, but there's only a 36.8% chance of that. And the third model, if I compute it, is 0.007, so there's only a less than 1% chance that that's going to be the better model. All right. And so how does that guide us? Well, one, it guides us. I mean, we can just straightforwardly pick the one with the smaller IC. We might also combine our models, right? Which is something referred to as an ensemble model, something that we'll talk about down the road. So in this example, we might say, okay, like that third model is like less than 1% that it's the best model, so let's get rid of it. Now, the second model does have a relatively high probability, so maybe I do want to include that. So what I could do is I could build an aggregate model, a combined model. We'll learn how to do this soon. And we can do it in a way that gives more weight to the first model, right? Because we feel more confident about that one. Right? Since that probability is close to 0.33, 0.33 is a third, right? We might weight the first model roughly 3 times more than the second model. Right? So that's the big picture idea. Now, just like a little bit of tweaking, a little bit of variations. The corrected IC is just a variant of the IC where we do a correction for finite populations. So, right, depending on when you're taking this class, you may or may not be in the process of taking Stat 514, right? If you are, then you're used to this idea of a finite population correction. And so formulaically, it's defined as, all right, we take that IC and we basically add this extra term to it. That extra term is 2k times k plus 1 over n minus k minus 1. And so we can see, right, we're actually, what are we doing? We're further penalizing for extra parameters, right? That k is the number of parameters. So adding more k is making the corrected IC even larger. So it's like, it's penalizing further. It's recommended by most practitioners that the corrected IC be used over the uncorrected IC. It can be shown it performs better in empirical simulations, but for large N, the two converge to one another. Right, N's our sample size, and so right, if it's better, then what is that saying? It's saying that right, how are they different? They're different in the sense that the corrected version has that extra penalty for more variables. So the implication of that is the uncorrected IC has the possibility of overfitting a model. That is, allowing variables to sneak in there because we didn't properly penalize them for entering our model. The last information criteria I'm going to talk about is the Bayesian information criteria, the BIC. Sometimes you might see it as SBIC, the Schwarz-Bayesian information criteria. It also penalizes more than the IC. It's roughly equal to k times log n minus -2 log likelihood. So in practice, of the three, the corrected IC is the preferred one. For time series and ARIMA models in particular, the corrected IC has been shown to work really, really well. When only IC and BIC are available, BIC is generally preferred. I believe the time series forecasting system does not do the corrected IC. So in that case, we're going to pick the BIC, which I think is listed as the Schwarz-Bayesian information criteria. And then, right, for those of you, you're getting closer and closer to graduation. If you wanted to do a little bit of extra reading, I kind of dug out maybe a couple of the easier to digest papers. If you wanted to dig a little deeper, at this point, it's maybe a little late for you to pick a paper to do a talk on. But if you're souring on your paper, right, here's some possibilities of papers that you could do a talk on if you were so inclined. And if not, still some interesting reading, especially if you find yourself in a job where you're using a lot of the IC and the BIC. All right, we'll be using it in some future labs, so I wanted to go ahead and talk about it now.